In this video, we're going to do an optimization question involving a poster. We want to maximize the area of the inner rectangle. So I want to maximize the area of the rectangle shown in red. It's the one shaded in. And I know that the overall rectangle has a length, which I'll indicate by L, uh, and a width, which I'll indicate by W. And since the overall area is 1014, I know that LW equals 1014. Now, this inner region, the printed region, will obviously have an area less than 1014, but I want to still maximize that value. Okay, well, what is the area of that printed region? Well, we see that the segment along the top has a length which is equal to this L minus 3 and 3. So in other words, it has a length equal to L minus 6, where L is the length of the bigger rectangle. And this inner rectangle here has a width which is given by the width of the overall rectangle minus this 2 and this 2. So it has a width of W minus 4, where W is the width of the bigger rectangle. So this is the area of the smaller rectangle, this equation shown here. That's equal to LW minus 4L minus 6W plus 24. Now, this equation here is not the one we want to end up with because we don't want two different variables. So what we do now is we look at this relationship here. Since LW equals 1014, that means L is equal to 1014 over W, or in other words, L is equal to 1014 W to the negative 1. So we plug in 1014 for LW, and then we plug in 1014 W to the negative 1 for L. And what we have now is an equation, an expression for the area, which is only in terms of W. So we can collect these like terms, the 1014 and the 24. We get 1038. Multiplying the 4 and the 1014, we get 4056 W to the negative 1 plus 6W. Okay, so we've got a very useful equation now that we can work with. However, we would like to have a domain as well. So we want to know the minimum and maximum values of W. Now, keep in mind what W is. W is equal to this, the length of that line segment. Okay, so that's what W is. And we want to know how small could it be and how large could it be. Well, in order to determine how small it can be, let's look at this exaggerated example here. The rectangle on the right is an example of us making the printed area as razor thin, as you can see there. Imagine it's razor thin. In other words, imagine that this width right here is practically 0. Well, the rectangle in question, as shown on this last slide, still has a 2 on the top and a 2 on the bottom. So this rectangle would still have a 2 on the top and a 2 on the bottom. So the W of that rectangle, the minimum W, would be a 4. And then there'd have to be some extra, there'd have to be some width to this blue rectangle. So we'll say it can't equal 4. Instead, we'll say that this width right here, the W value, we'll say that the W value has to be greater than 4. 4 would be the minimum, but it actually has to be greater than that. Okay, now, what would be the maximum value for W? Well, the maximum value for W would occur if we put all of the, if we made the inner rectangle razor thin, but shaped it the other way, okay, like it looks here, this would give us a maximum value for W. Well, you might think, okay, how long would that W be? Well, we'd still have a 2 on top and a 2 on the bottom, but now I want you to imagine that and we'd still have a 3 on each side. We have to have a 3 on each side. And now I want you to imagine that the L of this inner rectangle that I'm showing by a red spot up at the top, I want you to imagine that that's practically 0. Just for a second, let's imagine that it is 0. If it was 0, then that would mean that the L along the top would be equal to 6. Well, since that razor thin blue portion can't actually have an L of 0, we'll say imagine that it's greater than 0, which means that L has to be actually greater than 6. The reason I go through that is it's easy to imagine the smallest possible value for L being 6, and if we imagine that, then that's going to correspond to the greatest possible value for W, because L and W are inversely related. LW is equal to 1014, so the larger L is, the smaller W is, and vice versa. So they have an inverse relationship. So if I let L be as small as it can possibly be, and solve for W, I get W being 169. Well, since L has to be greater than 6, we can say W has to be less than 169. So I guess the outer bounds for W are that W has to be greater than 4, but W also has to be less than 169. Putting those together, we can say that our domain, I'll show it in a box at the bottom, is 4 less than W less than 169. So to put it briefly, the minimum value of W is relatively easy to see. It's got to be at least 4. The maximum value of W is not as easy to see. So what we do is we imagine the smallest value of L and try to determine the corresponding value of W. And that's what we get, 4 less than W less than 169. So now we can go back to our question and we can say A of W is equal to 1038 minus 4056 W to the negative 1 minus 6W over a domain 4 less than W less than 169. Well, we have A prime of W equal to 4056 W to the negative 2 minus 6. If A prime of W is equal to 0, then that would imply 4056 W to the negative 2 minus 6 is equal to 0, which would imply 4056 W to the negative 2 equals 6. Putting it in fraction form sometimes makes it a little easier to see the relationship. Multiply both sides by W squared. We get 4056 equals 6W squared. Divide both sides by 6, and we get 676 equals W squared. So we would get that W is equal to plus or minus 26. Well, it can't be negative 26, just common sense. It's equal to a length, so W can't be negative. But also, we could also say it can't be negative 26 because our domain was 4 to 169. So we're going to only focus on W equaling 26. And we're going to test 3 values in our area equation. We're going to test the W of 26 as well as the n values of 4 and 169. So if recalling that area as a function of W is equal to 1038 minus 4056 W to the negative 1 minus 6W, we can say that if we plug in a value of 4, we will get 1038 minus 4056 over 4 minus 6 times 4, which will ultimately equal 0. Plugging in 26, we would get 1038 minus 4056 over 26 minus 6 times 26, which is equal to 726. And plugging in a value of 169, we would get 1038 minus 4056 over 169 minus 6 times 169, which would equal 0. So we can see that our maximum area is 726, and it occurs when W equals 26. Well, what does L equal? You may recall from a while ago that L is equal to 1014 over W. So that would be 1014 over 26, which is 39. And so we can say, therefore, the dimensions of the poster that give the maximum printing area are 26 meters by 39 meters.